Good morning, students. Now onwards, we discussed about the chapter number 5, which is queuing theory. That will be discussed under 5 video lectures. The first lecture related to stochastic processes and queuing theory, its introduction. Second lecture related to arrival distribution as well as service times distribution. Third one, the classification of queuing models like finite capacity and infinite capacity. Fourth one related to the operating characteristics of queuing system. The last, the applications related to queuing system in different cases, right? So this class we are interested to introduction of stochastic process or random process and queuing theory. So what is a stochastic process? What is a stochastic process? Before going to the stochastic process, we should have to know where it can be applied. In many real life applications, our activities functioned with a time. Naturally, those models under stochastic model or those models are under stochastic process or random process. One example, the activities of a particular person from 9 a.m. to 12 noon, where he is moving, what he is doing, okay, and what activities completed, either positively, negatively, everything we discussed with respect to time is nothing but a stochastic model, right? One example I will provide it, the share of a particular bank, say SBI. The share of a bank may be increasing or stable or decreasing, again increasing with respect to different time intervals is under the nature of stochastic modeling. Stochastic modeling. So here I provided many applications related to stochastic modeling. One is population growth, communication and control, queuing theory, time series analysis, statistical physics, thermal noise, Brownian motion, the thermal noise, Brownian motion, short analysis. These are much more applications in mechanical and electrical people, okay. And again, inventory control, risk, insurance risk problems, the gambler's ruin problem. These are much more useful in business people or MBA people, and accepting sampling, dam problems and problems of genetics, okay. Communication networks, transportation systems, production processes, computer performance evaluations, internet applications, etc. so on, etc. so on. Now as the computer science students and information technology students, the scheduling of ATMs and internet applications and downloading of a particular files, that is called time sharing, okay, those are under the nature of stochastic modeling, under the domain of stochastic modeling. Are you okay? Right. So before defining the stochastic process, I would like to introduce the random variable. Of course this is an idea already you had, but as for our convenience, just we recall it. So what is a random variable? Really interested about the random variable should have to know random experiment. What is the random experiment? It has three conditions: repeated under identical conditions, all possible outcomes are known in advance, any performance of the experiment results an outcome that is not known in advance. From this random experiment we collect the sample space, generally sample space denoted by capital S or omega. So that sample space is the set of all possible outcomes of a random experiment. That's all possible outcomes of a random experiment, okay. So that sample space consisting numerical values, sometimes non-numerical values. If there is a non-numerical values, what are you doing now? Those non-numerical values are converting into numerical values with the help of the random variable. Okay, why should we introduce the random variable? Because non-numerical values of sample space converting into numerical values. Okay, I will provide the example right now. Suppose tossing a coin. What are the possibilities? Omega is equal to head denoted by h, t denoted by time. These are numerical values or non-numerical values? Non-numerical values. So what we have doing right now? Converting into numerical values. How? With the help of the random variable. See that if the outcome is the head, we assign 0. If the outcome is tail, we assign 1. So x of h is equal to 0, x of t is equal to 1. Okay, so omega be the sample space. Right now acting as domain set. Okay, and R is the real number set. That is right now acting as codomain set. So a real valued function defined on the sample space omega is called random variable. So what is the random variable here? A real valued function defined on the sample space. Agreed? Right. The same thing also shown as, let x mapping from omega to R such that omega belongs to capital Omega. What is the small omega? Sample point. This small omega acting as h or t. What is the capital Omega? Sample space. X of omega, x of h is equal to 0, x of t is equal to 1. What is the small x here? A real number set. Okay, so this x called as random variable. This x is called as random variable. That may be written as x is equal to x of omega very strictly. Alright. Suppose the same random variable is a function of time. This function of time is called stochastic process. That is, x is equal to x of omega comma t. Omega be the sample point. T is function of a time. T is function of time. X is equal to x of omega comma t is called a stochastic process. Generally that is denoted by x of t. What is the t here? T belongs to capital T is a time axis. Okay na? Simple example I will give you for stochastic process. There is a football game. 22 players acting in a ground, playing in a ground. Each team consisting 11 players, total of 22 players say. Suppose every player labeled with 1, 2, 3 etc. 22. That we may define as x1, x2, x22. For a player 1 in a different time periods with a different time epochs is movements in the ground. Moving towards the right, moving towards the left, moving towards the up and down etc. so on everywhere. So the movements of each and every player will be recorded. We collect all 22 players is collection of random variables, family of random variables indexed by a time parameter is called stochastic process. Okay, so that collection, the set of functions of all these 22 players representing a random process or stochastic process. Now we defined stochastic process generally. What is it? The collection or family of random variables that are indexed by a parameter such as a space and time are known to be stochastic process, are known as stochastic process. Are you okay now? See that x of omega comma t, omega is the space, t is called time. Okay, x of omega comma t, okay, omega belongs to sample space, t belongs to time parameter. Okay, so set of x of t comma t belongs to capital T is called stochastic process. So what is the basic difference in the random variable and the stochastic process or random process? In a random variable, a rule that assigns to a real number to every outcome of the random experiment. While in a random process is a rule that assigns a time function to every outcome of a random experiment. That's it. There is a rule assigned to every real number, a time. That's it. Okay. I will provide one example here. What is it? Observe the demand for week certain service of over a period of time. See that the demand is increasing, decreasing, stable with different time epochs. So these curves, these peakinesses with respect to time is nothing but under the model of stochastic nature. Okay, right. One more example here. Consider a experiment of tossing a die or throwing a die at time t is equal to 0. How many possibilities? The outcomes are 1 to 6. So we define time function t x1 of t is equal to minus 4, x2 of t is equal to minus 2, etc. x6 of t is equal to t by 2. See that every time the random variable functioned with t. Are you okay na? So the random variable functioned with a time is called a random process. That I written as the above set of functions x of t greater than or equal to 0 is equal to x1t, x2t, etc. x6t representing random process. Are you okay na? Right. Now classification of stochastic process. Generally, the classification of stochastic process depend upon state space and parametric space. State space is nothing but the sample space. Parametric space is nothing but time axis, time parameter or indexed parameter. So what is the state space? The set of possible values of any individual members of a random process. Means the set of all possible values of random process. Random experiment, like that, random process, right? What about the parametric space? The parametric space is nothing but the set of possible values of indexing parameter is called parametric space. Okay. Now state space and parametric space also classified into discrete and continuous. Suppose state space is discrete, parametric space is also discrete. That stochastic process is called discrete random process. Under this domain, there are many applications. The familiar applications here I measured as a brand switching model for consumers behavior. It is one of the application in business people, management people. And the second one is accepting sampling. This accepting sampling plays a vital role in statistical quality control for production lines. Right. Similarly, the state space is discrete, the parametric space is continuous. In this domain, our interest of queuing problems and inventory problems. The arrival entered into the system is discrete time periods. We provided the service to the each and every arrival is in a continuous manner. So parametric space is a continuous, the arrival is a discrete, right? So this is our interest, this domain. And the third domain, the state space is continuous and parametric space is, the state space is discrete and parametric space is discrete. State space is continuous, parametric space is discrete. Here in this domain, our problems are also queuing theory as well as inventory model, database management systems, storage of particular data into different clusters. We are talking about inventory control. And waiting time distribution of a customer is in a queuing theory, also this domain. Coming with the last one. What is the last domain here? Both are continuous. In both are continuous, coming a time sharing computer systems. It is very, very important. A time sharing computer systems. Okay, now here we go through that different examples for all 4 domains. Okay, it is very easy to understood at the different domains. Now coming with probability mass function, probability distribution function or cumulative distribution function. What is the probability mass function random variable? P of x is equal to probability of capital X is equal to small x is called a probability mass function under the properties of non-negativity, normality. Non-negativity means P of x is greater than or equal to 0 for all x. Normality means sum of the probability is equal to 1. Similarly, here the probability mass function P of x is equal to what is that? P of x1 comma x2 comma etc. xn is equal to probability of x1 is equal to small x1, x2 is equal to small x2, xn is equal to small xn, satisfying the conditions of non-negativity and normality with different time periods. What about this capital X1? Capital X1 defined as like that, x of omega comma t1. What about the capital X2? X of omega comma t2, like that, xn is equal to x of omega comma tn. Now the question is, what is small x1, small x2, small xn? The realization of the stochastic process. The random variable taking the value is called realization. Here also the realization of the random process or stochastic process is called small letters. Are you okay na? Right. Then come with the cumulative distribution function. What is the cumulative distribution function? In our random variable theory, f of x is equal to capital F of x is equal to probability of capital X is less than or equal to small x. Here also capital F of x1 comma x2 comma etc. xn is equal to P of x1 comma x1 less than or equal to small x1, x2 less than or equal to small x2, etc. xn less than or equal to small xn. What about the capital letters of x1, x2, etc.? Here we define. What about the small letters? The small x1, small x, xn, that is nothing but the realization of the stochastic process. Whatever we discussed in random variable, it is an extension of random variable. Is also stochastic process. In stochastic process. Are you okay na? Right. Now we are talking about basic process of stationary independent increments. What about stationary process? A stochastic process x of t belongs to capital T is said to be stationary increments if the sequence of random variables x1t, x2t, etc. xnt is same as distributed to x1 plus h, x of t1 plus h, x of t2 plus h, etc. x of tn plus h. What do you mean by identically distributed? Suppose the random variable x1 coming from a population with parameter mu comma sigma square, then the random variable x2 is also coming from the same population with the same parameters. Similarly, the stochastic process x1t, x2, sorry, x of t1, x of t2, etc. x of tn is same as x of t1 plus h, x of t2 plus h, etc. x of tn plus h. Both are identically distributed. Means what are the parameters exhibited by the first process, random process, is same as the second process. There is no change of the parameters. Okay na? Right. Independent increments. In independent increments, suppose we consider time axis. Time points are t0, t1, t2, etc. tn. At t0, the realization of the stochastic process is xt0. At t1, the realization of the stochastic process is xt1. Similarly, at tn, the realization is x of tn. Right? Now, the difference between the realizations like x of t1 minus t0, comma, x of t2 minus t1, etc. X of Tn minus Tn minus 1 are independent. What it could mean in a practical? Suppose there is a ATM counter. ATM counter. In that counter, at 9 a.m., that is T0, no customer entered. After 1 hour, means 10 a.m., that is T1. The occurrence of customers arrivals between this time interval, say 5 members. 5 members. So, x of T1 minus x of T0 is equal to 5. After 1 hour again, 11 a.m., there may be 9 members arrived. So, x of T2 minus x of T1 is equal to 9. So, these 9 members is independent of the previous 5 members. The previous 5 members. That is called independent increments. X of T1 minus T0, comma, x of T2 minus T1, etc. x of Tn minus x of Tn minus 1 are independent of. Okay? Means the occurrence of the events any time interval are independent, very simply. Okay? Now coming with the stationary independent increment process. Any stochastic process satisfying the condition of stationarity and independent increments, previous two processes, that process is called stationary independent increment process. Very strictly, the stationary independent increment process is the occurrence of the events is depend upon the length of the time interval only, but not where it is located. Where it is located. So, stationarity is existing as well as independent increments also existing. So, any stochastic process satisfying these two conditions, that is called stationarily independent increments. Stationarily independent increments. Okay, right. Now, I would like to introduce two more important processes, that is called Markovian process and counting process. What is a Markovian process? Students, listen here. Before introducing the Markovian process, I will give you one example. As a teacher myself, dear student, tomorrow evening I will take one class in video lecture. You the students, you trust it, you make yourself is a convenient to ready for the class. That statement actually delivered from myself today 9 a.m. today morning session. Afternoon at 12 noon, my statement is modified as, dear student, tomorrow evening I don't want to take a class. That class will be preponed in morning. So, you the pupil trust the first statement or second statement? Naturally second statement. Naturally second statement. Again, my statement modified as, students, I don't want to take a class tomorrow due to some reasons. The class is cancelled. So, you the pupil trust the third statement or second statement or first statement? You trust the third statement. So, what happens here? The future value of the stochastic process is depend upon recently known value, but not past values. But not past values. So, what are the past values? Tomorrow evening is the class. Then tomorrow morning is the class. Then class is cancelled. So, which is the statement is trustable? The last statement. the same thing discussed in a Markovian process. See that. The future value probability of x of tn plus 1 is the future value is depend upon recently known value x of tn but not the past values. So what are the past values? At t0, at t1, at tn minus 1, recently known value tn. So future value is tn plus 1. So tn plus 1, the realization of the stochastic process tn plus 1 is depend upon recently known value but not past values. Agreed? Good. This Markovian process actually plays a vital role in queuing theory. Now coming with the counting process. Here there is a small typical mistake, counting. Counting process is very easy. Why? Because the arrivals entered into the center like ATM counter is integral value or not? The number of customers entered, integral value. So any counting, any random process is said to be a counting process should be n of t greater than 0. That should be some positive integer, right? This n of t should be integer valued. And third one, the time epochs s and t. S is say 9 am, t is say 10 am. The occurrence of the events in 10 am should be greater than occurrence of the events of 9 am. That is n of s less than n of t. N of s is less than n of t. So any stochastic process satisfying these three conditions, that stochastic process is called a counting process, generally denoted by n of t. Right? Now we discussed as counting process, Markovian process, stationarily independent increment process, classification of stochastic process, and definition of stochastic process. These five things will be useful in our queuing theory. Right? What is a queuing theory? Here queuing theory is just for a waiting line. Why we are waiting? Demanding the service from service station. Simple example. I would like to fill the oil, petrol in my two-wheeler. So what I am doing? Go to the petrol bunk. Before entering the petrol bunk, okay, once I entered in the bunk, there will be some vehicles waiting for filling the oil. So there is a big queue. So the mathematical modeling of this queuing system is called queuing model. Mathematical representation of this queuing model is called queuing system is called queuing model. So a queue is a waiting line of units demanding service at a service facility. What is the service here? Filling the oil. Okay, the mathematical representation of a queuing system is known as queuing model. Why? Because we are going for the queuing model. Because predicting and evaluating the performance of the service station or queuing system. How much time is I want to be wait for filling the liquid, filling the oil. That is called predicting. What type of service adapted to the customer? That is called performance. So that predicting and evaluating the system performances can be analyzed under the queuing system. Are you okay na? Right. Now what are the objective of the queuing model here? The objective of the queuing model is to find the optimum service rate and the number of servers to that the number of servers so that the average cost of being in the queuing system and the cost of service to be minimized. So they would like to provide the best service, optimum service with low cost is the objective of the queuing system. Now many applications in a queuing system, what are that? That is a business, in a banking counters and booking counters, etc. so on, under the model of queuing systems. Similarly, industry, servicing of machines and layout of manufacturing systems. In a public sector, railway reservation counters, post office counter, we are waiting for service, we are in the queue. Similarly, transportation and traffic control at airport and pub and harbors, suppose check in and check out in airport, we are waiting for check in and we are coming out from the airport, we again check out, we are waiting. Wherever the waiting, there is a queuing system. Suppose the ships loading and unloading at harbors, again under the model of queuing system. Similar with telecommunication applications, internet applications, traffic flow control, ATM scheduling, satellite communications, and computer systems. In a computer system, the sequence of computer operations and predicting computer performances. Suppose we would like to download a particular file, the bandwidth is high, the download time is reducing, the bandwidth is low, the download time is increasing. Okay, it is also depend upon system performances. Similarly, everyday experiences, what are the experiences? Restaurants, doctors, clinics and hospitals, etc. so on, we are waiting for service. Are you gonna? Now once you know that the familiar applications, what about the general diagram of a block diagram of queuing process? The block diagram of a queuing process is the customer entered is called arriving the customer, and the waiting line is nothing but queue, and service we adapt to the customer is called service station. After the service, the customer leaving the station is called customers leaving, exiting from the system. So arriving the customer is one component, and queue discipline is the second component, service mechanism is the third component, and behavior of the customer is the fourth component. So what are the main components in the queuing system? One is arrival process, second one is service process, third one is queue discipline, the fourth one is behavior of the customer. These four components generally plays a vital role in queuing system. So arrival and is a queuing model, okay, queue discipline and service mechanism, customer of behavior, right? The fundamental components of queuing process. The input process are arrivals, service mechanism, queue discipline, customer behavior. So input process means how the customer entered into the system. What is the probability distribution of customer? Okay, what is the arrival rate of a customer? Okay, so all these things will be discussed in arrival process or input process. Generally, the arrival distribution is Poisson. P and T is equal to e power minus lambda t whole power n by n factorial. You know that in a Poisson distribution, P of x is equal to e power minus lambda power x by x factorial. X is the random variable here. Here n is nothing but the number of customers. What is the t here? T is the length of the time interval or time interval 0 to t. N is equal to 0, no customer. N is equal to 1, 1 customer, 2, 2 customers, etc. so on. Similarly, and second, what is the inter-arrival distribution? Inter-arrival distribution means service time distribution. The service time distribution is the exponential. Exponential distribution theta into e power minus theta t. Of course, we discussed in the classroom already. Third one, mean arrival rate and the inter-arrival times. All these factors, all these characteristics will be discussed in the input process. Of course, this will be discussed later also in arrival distribution, and the inter-arrival distributions will be derived in the next lecture. Okay, right. Now coming with the service mechanism. Okay, service mechanism is nothing but what type of service we adapt to the customer when he is in a waiting line, right? Okay, now in a service time distributions with single channel, multi-channel, multi-phase, etc. so on. Now come with the point here, what is the service time distribution? Here single channel facility or one queue, one service station. Suppose the arrival entered in the system, there is a entered into the queue, and so entered in when waiting in a queue line, we adapt to the service to the customer after service exiting from the service station. The best example is a library counter. There is a single counter, there is a single line, each and every student come to the counter and submit the book and return the book, or return the book and collect the new book, etc. Everything is happens to a single counter. That is one channel facility or single channel facility. Now coming with one queue, several stations. See that arrival entered in the system, there is a queue. After the queue, there will be 3 service centers. Service center 1, service center 2, service center 3. For example, we entered in the petrol bunk. There is a big queue, but the filling stations are 3. Service center station 1, station 2, station 3. That is called one queue, several service stations, service facilities. Now coming with the multi-channel facility. What is a multi-channel facility? In a multi-channel facility, arrivals entered in the system, there will be multi-queues, multi-service channels. After the service, exit from the system. This is the one example for railway reservation counters. Entered into the system, there will be first counter, second counter, third counter. At every counter there will be a Q1, Q2, Q3. Right? Now fourth category is multi-stage or multi-channel facility. What is the multi-stage, multi-channel facility? For example, we are going to the bank. I am the person interested about withdraw the money. What I am doing? Go to the first counter, collecting the withdrawal form. Right? Once we fill the withdrawal form, the same form submitted to second counter. The bank people collected my paper and they issued one token. Keeping that token at my pocket, I am waiting some time, and third counter person is called me for giving the money. So I am the customer taking service in how many phases? 3 phases. One phase is withdrawal form collection. Second phase is collecting the token. The third phase is collecting the money. So one customer getting the service into 3 phases. This is arrival, service station 1, service station 2, service station 3, etc. so on. Okay, so we adapted the service to the customers into different structures we will discuss in service mechanism. In that, the distribution of customer service, the distribution of time taken to each and every customer, and the average number of customers being serviced in 1 unit of time at a service station, etc. so on will be discussed. Right? Now third component. What is the third component here? Queue discipline. Here queue discipline is nothing but the rule to form the formation of a queue, and the rule to selecting for a service when they are in waiting line. Now the general queue rules are first in, first out. Suppose the customer entered into the service station, he is waiting for service. Similarly, after the service, he leave from the room. First in, first out. Okay, simple example, I would like to call the attendance in the classroom. Number 1, number 2, number 3. First in, first means maintain order. Second one, first in, last out. Suppose FCI godowns, Food Corporation of India godowns. The first rice packets we put in the corner of the room, but not the first place, the entrance. So first packet keeping in the corner of the room. First in, last out. Suppose unloading the room, empty the room. What I am doing? Shall we take the first packet? No. Which packet is entered in the last? That packet will be removed the first. Okay. Third one, service in random order. Suppose I would like to ask the question to the student. Roll number 48. What is the answer for this question? Roll number 32, what is the answer for this? Roll number B6, what is the answer for that? Right? So service in random order, selection random order. Now last one, priority service. Priority service representing, suppose I want to get the ticket for the movie, go to the theater. There is a big line, but I am very happy. One of my friend is working in the theater. I call to my friend, get the ticket, means priority. Means priority. So the queue discipline may be existing any one of these four: first in first out, last in first out, service in random order, and priority. Okay. Now customer behavior. In a customer behavior, generally we talk about barking and rinsing and joking and priority. So what is the meaning of that? Suppose some customers entered in the waiting line, but they are leaving their patience, immediately refused it the service. Coming to the out, discouraging. Suppose some customers are moving one queue to another queue because second queue may be size is less. Right? Some customers see that there is a big queue and the room is filled with all the customers. There is no space to waiting, so that they don't want to enter into the queue. So different attitude of the customers entered there. Those attitudes also discussed in customers behavior. Are you okay? Right. So what are the main components? Input process, service mechanism, queue discipline, customers behavior. Once we describing all these in queuing system, now the solutions of the queuing system. That solution generally depend upon transient state solution and steady state solution. Transient state solution is nothing but the operating characteristics of queuing system are functions of time, or depend upon time. Steady state solutions representing the operating characteristics are independent of time, no way concerned about time, is called steady state solutions. As t tends to 0, as t tends to infinity, these operating characteristics are independent. Right? So transient state solutions are depend upon time, and the steady state solutions are independent of time. Are you okay? Right. Now the last one. What is the last one here? Traffic intensity and Kendall's notations. See that in a year I discussed about P and T. What is the P and T here? The probability of n of t is equal to small n. What is the n of t? Counting process, just I discussed, right? N of t is equal to n. What is the small n here? N customers. See that P and T is equal to the probability that there are n units in the system at a time t. Okay, the solution is independent of time, means as t tends to 0, the d by dt of p and t is equal to 0. In a steady state solution, this p and t is equal to 0 as t tends to 0, means independent of time. Okay, right. Now coming with the traffic intensity. What is the traffic intensity here? Traffic intensity is nothing but the ratio between arrivals as well as service. Arrival rate generally denoted by lambda, service rate generally denoted by mu. Lambda by mu talk about traffic intensity. This traffic intensity plays a vital role in further studies. Just I defined right now. Okay, right. Now coming with the notation. It is important. What is the important? Kendall's notation. It is very simple. The Kendall is one of the statistician representing the queuing system into A, B, C, D, E. A representing arrival process, probability of arrivals. B representing service process. C representing the number of service channels or service stations. D representing the capacity of the system, either it is a finite or infinite. E representing queue discipline. So these 5 alphabets representing the queuing system. Once again, A arrival process, B service process, C number of service channels, D capacity of the system, and E, what is the E here? The queue discipline. So this representation useful in understanding a queuing system. Okay na? This is the class related to introductions to stochastic process as well as queuing theory. Before leaving that, I will summarize it. So, what is the stochastic process? Right? What about the nature of the stochastic process? Probability mass function and cumulative distribution function, stationary independent increment process, and Markovian process, also counting process. Then we introduced queuing system, the fundamental components of queuing system. What are the fundamental components? Arrival process, input process, service mechanism, and queue discipline, consumers behavior, or sorry, customers behavior. After that, the solutions of the queuing system: steady state solution, transient state solution. Then we talk about notation of queuing system. Are you okay? Right. Now shall we close this session, and the next lecture will derive into the next class. Thank you very much.